FAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede 5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
This is on drag reduction. Every airplane can benefit by reducing the drag of the aircraft itself. A significant performance gains can be obtained from this. Sometimes subtle, small, but add them all up and they can add into something quite large, quite beneficial. If you can reduce the drag of the airplane, and the home build, of course, you have a great deal of latitude to doing that, but even store-bought airplanes have the flexibility of being able to be cleaned up. But if you can reduce the drag of it, not only will you increase the cruising speed and the top speed, but you'll actually increase the range, in fact, by direct proportion to what you do in improving your cruising speed. You'll improve the rate of climb of the aircraft. You'll improve its endurance. You may even improve its takeoff and stalling speeds. In fact, you can even do so much sometimes as to improve the controllability and the handling characteristics of it by allowing the control surfaces to work better because you have cleaned up the aircraft and reduced the drag associated with something in that particular region. So reducing the drag of the airplane is very critical and very important to be done. And there's a lot of things that can be done. The late Dr. Raspet from Mississippi State used to take an airplane up, and he used to put tufts or pieces of yarn all over the entire surface of the airplane, top of the wings, bottom, fuselage, all the way around. Take it up, do flight test work with it, and photograph or look at the tufts themselves. And where you have flow separation, you'll see the tufts swirling and shaking and vibrating quite a bit. And if it's a big region, of course, you know that's a large source of drag. What he would do is find the area that caused the greatest amount of drag and do a lot of work to improving it or maybe even eliminating it. Now the second worst thing became the worst, and you do that in the third and the fourth and so on. And you can keep going until it gets to the point, of course, where you feel that the gains you've obtained from it is adequate enough, and you can stop at that particular point. But most any airplane can be improved and changed, and sometimes these are very simple little things to do. I guess one thing we really want to understand is the three basic types of drags that are associated with an airplane. The first is skin drag. This is the actual drag that the air molecules rubbing against the skin surface of the airplane, the wing, the fuselage, the tail, the belly, wherever it is. When they rub up against it, they actually slide against the metal or fabric or composite structure, whatever it is, and produce drag. Skin drag, sliding drag. The skin drag can be broken down into two basic types, laminar flow and turbulent flow. Now the turbulent flow is not actually stall or separated flow, but it's the boundary layer itself that is turbulent. If we would take a look at a standard modern type airfoil, if we would look at a laminar airfoil section, we would find one where the maximum thickness is generally around the 40, 50, or 60% point of the cord. And what we will find here, as the air comes along and flows over this particular wing, the very thin layer of air, and this is a real thin layer of air. If this was a 4-foot cord, for example, about halfway back, the thickness of the dime would be how thick this boundary layer is. And it's a laminar boundary layer. As it gets further back and goes into the turbulent boundary layer, it gets much thicker. And by the time it gets to the trailing edge, it may be a 1/4 inch thick or 3/8 of an inch, or if it's a very dirty airfoil section, maybe even a 1/2 inch thick will be what the boundary layer itself is. The layer that actually bounds right up against the surface. But in the early portion here, if the wing is very smooth, we will have what is known as a laminar boundary layer. Now this, if you would look at it in a magnified view, if we would take a look at what the air is doing here, the airstream, and this would, the vector of it would denote the speed of it. And if we would take a look all the way down as it gets closer to the surface, we would find that these streams are flowing along very nicely, but each time they're getting a little bit slower and slower as it gets closer to the surface here, until when they're right next to the surface, they're quite slow. So if we plot this out, we would see that we would have a gradient that would look like this. But the key thing is that all the streams are nice and parallel and smooth, and the air is flowing very nice. Now this would be considered a laminar boundary layer. Now further back here, once it gets into the turbulent boundary layer, we would see that on that surface, if we would plot it, here would be a stream up here, a nice free stream, but as we got further down, they would start to become very turbulent. And the airflow would start not only slowing down quite a bit, but not being parallel, not being even streams and so on. Now what's important about it is the fact that this turbulent boundary layer, besides being thicker, and therefore the mixing of the air would make it thicker, this, the laminar boundary layer, has 1/7 the amount of drag that this turbulent boundary layer has. So obviously if we can have an airfoil, and the more laminar flow over it, the less drag that this whole airfoil will have on its profile drag or skin drag. So it's quite important to try and have a very nice laminar flow as far as we can. Now what has happened in trying to obtain this laminar flow section is this. As the air flows over the wing, it starts to speed up. As long as it is speeding up, or as the air pressure gets lower and lower as it goes over, it will tend to stay in the laminar flow, providing, of course, that the surface itself is nice and smooth. But as it gets over to a certain point in here, finally the pressure does not decrease anymore, the speed does not increase anymore, the speed starts to slow down. As soon as it does, we get a little transition point, and we'll have a turbulent boundary layer from this point on. It'll actually snap right at one particular spot and get bigger and go on back through there. The further back we can get it, the lower drag the airfoil section itself will be, but the more sensitive the skin of the wing will be. A little bug, a crack, or a gap or something like that will immediately trigger off the laminar boundary layer and make it turbulent right away. If we have something where it's laminar up to 30% or 40%, that can tolerate some pretty good bugs and some deforming on the wing itself. Maybe not a big rivet head or something like that. We get something that big up there, it's going to kick off this boundary layer, make it a turbulent boundary layer. And worst part is, not only does it just go straight back, it spreads out at an angle, so it goes span-wise as one rivet in this portion would do. So they found that laminar airfoil sections with 40, 50, somewhere in that degree of percent back will give us good performance in everyday real world conditions. But this kind of boundary layer is something we'd like to have. On a fuselage, if it's a sailplane or a pushing airplane, we may have that in the early portion of the fuselage itself, but as it goes back, of course, it'll become a turbulent boundary layer, and the tail sections and the belly and all these things will add up the same sort of way. So the skin friction, the profile drag, if you want to call it that, is important, and this is something that we have to have. The air is molecules, it has friction, it's viscous. When you look up the chart and you look up the drag coefficient in airfoil, and it will say 0.006, for example, what it is really saying is that is the total profile drag, skin drag of that airfoil for that particular shape. So that's the number you see when you look up your particular charts in there. The second type of drag you have is base drag. This is the drag that you would have off the back of the fuselage, for example, if it was shaped maybe streamlined in the beginning in here, but then had a very blunt section in the back. As the air flows over this whole surface, it cannot go around that corner. It will separate from here. This is not just turbulent now, this is total separation. You'll have all kinds of turbulent air in here. This portion right in here is considered base drag. And it depends on the shape, it depends how far back it is, it depends on a lot of things as to what the actual drag coefficient of that is. But anytime you have a blunt object, anytime you have a shape, if you have, for example, a windshield sticking up here on an open cockpit, the drag behind this open windshield is your base drag. It's total flow separation. It's a low pressure suction back in here. It's trying to suck the structure back, pulling the airplane back, and increasing the drag on it. The third drag that we would have is induced drag. Now this drag is the drag that you get by just obtaining lift. I mean, to just get lift, and lift is something when you're going down horizontal through the air and you want to produce a force upward, you get a vector that's 90 degrees from the stream of which you're flowing, or the way you're flowing. But just to get that, to be able to change the momentum, to be able to deflect the air or water, whatever you want to do, you're going to get a component that is always deflected backwards, and if you break it down, you'll have lift and drag. To see this a little better, let's take a look at this example here. Let's assume we had a garden hose with water on it. And let's assume we took a plate and we bent it like this, 90 degrees. We took our stream of water and we shot it at it. Turn the stream of water on it, and of course it would turn and flow straight down in here like this. Okay, Obviously, this plate is going to want to be pushed. And what is going to be done, if we could neglect the friction of the water against the thing, would be a force that is exactly 45 degrees or split between this angle. If this is turned 90 degrees, this will be 45 degrees off in that direction. And that can be broken down into two components. One force this way, one force this way. So these two essentially mean what that total resultant force is. This one, of course, we can call our lift. This one we'd have to call our induced drag. Just by the fact that we've actually turned the water or air or whatever it might be, the fact that we've turned it and deflected it, we will get a resultant force off this way. The vertical one, 90 degrees to the flow, is lift, and the one parallel to it is the drag. If we take a look at an actual wing, we don't want to deflect it full 90 degrees. We take an airfoil section like this, and here comes the air flowing along at it like this. When it gets through, it goes off downward here at some particular angle. This angle in here like that. The fact that it deflected the stream means that we will get a resultant force up in this direction. Again, it can be broken down into a vertical force, which is lift, and a backward force, which is the induced drag. Yeah. Even if this air was made out of ball bearings and Teflon, and so it had no viscous, no skin friction, nothing like that, and you had no base drag because you brought it together at a super point in the back, even if it was frictionless air, just the fact that you deflected it automatically gives you induced drag. Now we know how to control induced drag. We do that by making a wing have a long aspect ratio, long span, short chord. And what that means is for a given amount of area, what we're trying to do is, as we flow through the air, is we're trying to deflect a very wide piece of air very slightly down. The smaller we can deflect it down, the less the induced drag itself will be. If we take that same area and make a short span, big chord out of it, same area now, what are we doing? We're working with just a narrow stream of air. We have to deflect it a lot more just to get the same amount of lift. If we try to deflect it only the same amount as a high aspect ratio one did, we would have the same induced drag for that little portion, but the total lift and the total induced drag would be very, very small because we used all that area and just deflecting a very, very little bit of narrow piece of air. So the ideal thing is to make a long span, and the longer the span is, of course, the better your reduction of induced drag will be. Sailplanes, this is very, very important for them. Of course, what do? They make very high aspect ratio wings out of it, very definitely. When you're dealing with jet aircraft that are going quite fast, induced drag is not as important because you're up into high-speed conditions where you don't want to deflect very much air because you're going so fast, you're going through so much air that you just need to deflect it a very slight amount, and that'll give you all the lift you need for the weight of your airplane, and therefore you don't have much induced drag. And then profile drag and skin drag and base drag, those are the things that really count and are important to you. To have induced drag reduced to its minimum, the ideal thing is to not just take a certain width of air, a certain tip-to-tip span and deflect it, but to deflect it in an elliptical distribution. More in the middle and gradually in a nice elliptical pattern towards the tip. You can do this by having an elliptical shaped planform of the wing. But if you don't watch out, if you change the size of the chord, the camber of the wing as it gets to the narrow tip to it, or if you put a little twist to it, even an elliptical wing will not give you an elliptical lift distribution. But it's been found through thousands of tests already that what we can do is go to a tapered wing and maybe do a little bit of twisting to the wing or something like that and get a near elliptical lift distribution with very, very little, practically none measurable loss of efficiency by not being purely elliptical. So theoretically, an elliptical lift distribution is best. You don't have to be that exotic about it. A tapered wing, even a rectangular wing, will not give you an elliptical distribution, but your induced drag may only be 5 or 8% higher than it would be if it was elliptical. And the time you have to worry about it is when you're down at max LOD or minimum power required for flying, not necessarily in cruising. Best rate of climb, cruise performance, those are important for induced drag. If that's not real critical, then a straight tapered wing, a rectangular wing, not a tapered wing, is going to be adequate for you. But we know how to handle induced drag. You do that primarily by your planform. Now, we see a lot of things sometimes where we're talking about the tip vortices, and this is the induced drag. It's not the vortice coming off the tip that's actually sucking the airplane back. You never hear of a wingtip being sucked off because the vortice was so great or the induced drag was so high. That's just the final end result of deflecting all this air down. We can see the ends of it, and it makes this vortice. It's very critical. I mean, we can see it. It causes turbulence and wake turbulence for us behind, but that's not necessarily the thing to be concerned about, trying to eliminate that vortice. You can't really eliminate it anyways. But what you can do, of course, is have a very, very broad span out there, and that will give you your lowest induced drag. If we take a look at a standard 4-place high-wing tricycle gear single engine airplane, a normal store-bought type design, and take a look at seeing what would happen if we could clean up some of the various factors on the design itself and see what it would do to our performance. If we would take a look at it and just assume that this particular aircraft for its size has a total drag of 467 pounds and has a cruising speed of 118 miles per hour. Now, let's take sort of one thing at a time as we go along here. Let's start reducing the size of the cowling inlet itself and maybe the exhaust. Clean up this portion right in here and maybe do a little cleaning up of how the exhaust goes out there. If we would do that, the reduction of drag coefficient would be 0.05. This is based upon its own area, so these are relative numbers. Don't worry about them as exact. But the end result is it will actually reduce the drag 6 pounds at that particular speed. Now the total drag is only 461 pounds, and the speed has gone up to 122 miles per hour. Now, if we would take that and do something with the back window in here, maybe straighten it out, make sure we have nice, good detached flow onto it at all times. That reduction in drag coefficient would be 0.07. It would reduce it another 19 pounds of total drag. The total drag would now be only 442 pounds, and the speed would go up to 129 miles per hour. Okay, now let's assume that we start working on the wing interference over in here. Let's assume we cleaned up this portion in here because we had a round fuselage. So we're going to square it off. We're going to take care of the interference back in here that we had with the round fuselage meeting the trailing edge of the wing. We had a reduction in drag coefficient of 0.057. 10 more pounds of drag is reduced. The total drag is now 432 pounds, and our cruising speed's gone up to 133 miles an hour. Let's assume we went ahead and took the main tires off and used the same size wheel but went to smaller overall diameter, overall shape, lower profile type tires on there. Just that item alone, just taking that alone, has a reduction of drag coefficient of 0.669, again based upon its area. A total drag of 16 pounds are reduced. The total drag is down to 416 pounds. We now have gone up to 139 miles per hour. Okay, let's start working on the nose wheel. Let's change the nose wheel shape. Get rid of the big strut. Put a nice small little strut in there and put a smaller nose wheel assembly in here, one that has good flotation on it so we still can get in the smaller fields with it. Our drag reduction on the CD is 0.669. We've reduced another 24 pounds. Our total drag now is down to 392 pounds. Our speed's up to 147 miles per hour. All right, let's take these struts that we had on here and we really clean them up. Let's put nice fairings on here. Let's put nice streamlined fairings on these struts. Make them good airfoil shape. The drag coefficient on that was 1.0. We now have reduced the drag 25 more pounds. Our total drag is only 367 pounds. Our speed is picked up to 155 miles per hour. All right, what else can we do? Okay, let's get rid of all the rivets on the wings. Let's make this a nice, super smooth fiberglass wing, composite wing, or nice smooth metal wing, getting rid of just the rivets. Now, we haven't changed the airfoil at this point. We've just gotten rid of the rivets alone. The drag reduction on that is 0.005 on the coefficient. The total drag reduced on that surface alone is 35 pounds. Our total drag is 332 pounds. Our speed's gone up to 165 miles per hour. All right, now let's assume we got rid of the 4-digit airfoil section that was originally on this airplane and we make it a nice, smooth laminar flow section on here. Our drag coefficient reduction is 0.002. We've gotten 14 pounds less drag from it. Our total drag is only 318 pounds total. We're up to 169 miles per hour. All right, let's get rid of these wing struts. Itself, let's make this a cantilever wing. Over here, get rid of the struts, the interference on the struts and everything else. We've reduced the drag coefficient another 0.20. Another 39 pounds is off. Our total drag is only 279 pounds. Our cruising speed's 180 miles per hour. Same identical engine, same basic weight, same everything else the same. We haven't done anything with the span of the wing, the aspect ratio. We haven't done anything with the plan form. You can see these are just a bunch of relatively minor things. If you take a look at this airplane aesthetically, you wouldn't see any real significant difference in the way it looks, but it is cleaned up. Dr. Raspet did the same sort of thing with the Navion, with the Twin Bonanza. For example, in the Twin Bonanza, he had an airplane there where when you looked at it, it looked almost identical, a little smoother, almost identical, except it didn't have a dorsal fin. He went from something like 161 mile an hour cruising speed up to 192 mile an hour cruising speed. Obviously increased the range well over 20%, increased the endurance, increased the rate of climb, reduced the single engine control speed. All of the various factors were done, and yet the airplane looked almost fundamentally the same. Didn't do anything to the main spar, the main airfoil sections or anything like that. Just stayed with the basic airplane and cleaned it up as he went along on it. So a lot can actually be done on an airplane to improve its performance. And this is something, of course, we can do with the home-built airplane, one that maybe you're designing, maybe one that you're working on right now, or maybe one that you're flying, even the one you have flying right now. You don't have to necessarily go to a bigger engine or some exotic engineering device on the thing to try and get more performance out. Clean it up, get it smoother, get it better, and you will end up improving the performance of your airplane appreciably. When we start to take a look at the drag coefficient of various shapes and objects, for example, in Horner's Fluid Dynamic Drag book, which is a tremendous wealth of information of drag coefficients of various shapes and items, we have to remember that what we're really looking at here is the particular drag coefficient for that given item, and you have to be very careful to look at the text to determine what the drag coefficient is based on, what area it's based on. For example, on a wing, they always give the drag coefficient based upon the plan form area of the wing, looking at the wing from the top, what the total wing area is. But on most other items, they'll give the drag coefficient based upon the frontal area. You could actually give the drag coefficient of the airfoil based upon its frontal area if you wanted to. The actual CD number would be larger because the area is smaller, but the summation, the total of the drag coefficient times its equivalent area will give you the flat plate area, or the equivalent flat plate area, or the F number, whatever way you want to call it. But it's that summation of those two items that is the real working number that you want to go with. So when you're dealing with the drag coefficient, be sure you understand what particular area it's dealing with. And then remember that sometimes you can have something that has a larger coefficient of drag but less total drag. For example, a round ring going through the air, a round plate just shoving through the air over here will have a drag coefficient maybe of somewhere in the neighborhood of 0.9 as an example. But if you put a hole in it, that drag coefficient may go up to 1.1, 1.2 even. But because there is so much less area being exposed of this washer going through the air, the total drag will be less than that of the flat plate. So the drag coefficient is important, but don't get misled sometimes, because sometimes something with a little higher CD that has a lot less area has less total drag to go with it. But let's take a look at a standard airfoil, for example. And if we would consider this airfoil to be a normal tail surface, for example, a 4-digit section, a 0012, a symmetrical section 12% thick, we would have a normal CD of this to be around 0.009. Now, if we have to put a control surface on here, an ordinary type of plane control fits back in here, and let's assume it's 20 or 25% of the cord, we'll find out that the drag coefficient in this actually goes up to a CD of 0.015. Now, if this particular section is what we have to have because it's a control section, there is something we can actually do to reduce it. We can take this particular gap right in here itself, and instead of having what was originally just a straight one that we cut into this, we do one of two things. We either reduce this surface so that it is slightly smaller, give you an expanded view of it. If this is the control surface itself right in here, and this was the continuation of that airfoil here, if we reduce it down to here like this, we will now have a CD of 0.0093. A little bit higher than the absolutely straight smooth section, but not much. We have reduced it quite a bit. This is a little bit harder to build, actually, when you have to reduce it from the normal thickness down to here, because you'd like to put a spar in there. You'd like to be able to have your control hinge brackets attached to it and everything else. So that is somewhat more difficult to work with. What I prefer to do is to keep the main part of the surface the same, let it come back in here like this, let the spar be in here, get your full maximum thickness out of it, and then change the actual control surface itself. Go to something that is larger, that sticks up out of the surface and goes back down to the same trailing edge. Now, I'm exaggerating this thing quite a bit in here. It doesn't have to stick up very high to it. For example, if this happens to be on a wing that has a 4-foot cord, and this might be the aileron on here, this amount that is sticking up here might be only 1/8 of an inch. But what it does is, as the airflow, as the boundary layer comes across in here and has to jump this gap, it has to pick up and increase in speed and go over this surface because of the curvature portion. And as it does, it gains energy and stays attached to it. But if it has to skip over it and just stay at the same particular height, it has a good tendency of tripping off quite a bit and becoming more turbulent and therefore higher drag with the thing. So a simple thing like controlling the gap that you actually have on the surface itself is a definite benefit in reducing the drag of the particular surface. If you look at Horner's book, they show you some charts in there of what it does. In other words, if your gap or your increase that you have of the control surface is not exactly the optimum that they predict, you still have made a reasonable reduction in the drag to it. Even just taking and putting a seal across there, or a felt strip, or some sort of gap in there, or like on a J3 Cub where you have to stabilize the elevator and an open port, putting a little gap in it, that will actually reduce the drag. Not as effective as this, but it will reduce the drag. So a number of these little items that you have to look at very closely. They're simple to do, but they make the difference between having higher drag or less drag. And the same thing like in an engine, an automobile engine. You don't want to put real poor oil in it that doesn't have low friction on it. It may still be pretty slippery, but it is not as good as the best. Every time you can reduce the friction, whether it's inside the engine or reduce the friction on the outside of the airplane, you're going to get better total performance out of it. Let's take a look at wingtips now and study them a little bit. We've heard a lot of things called Horner wingtips and stuff like that. Actually, Horner did not develop any particular airfoil or wingtip himself. What he did is he did a study back for the Air Force in the late 40s and studied various types of wingtips and came to the conclusion that particular shapes would give some better results than others. If we take a look at an ordinary wingtip, let's take a look at it from a head-on view. Let's assume that it was just a nice rounded one in here. Let's assume we have another one that is squared off in here like this. What happens is, as the wing is flown along with the angle of attack and the higher pressure on the bottom, it wants to, of course, come around and meet the low pressure air up on top, and this begins the start of the vortice. If this portion is very round, very smooth, it will actually want to get around there quite easy, and the center of the vortex will move in. It'll move in from the actual real physical tip. So theoretically, your aspect ratio should be based upon where the center of your vortex is, and it is less than what your real geometric aspect ratio is. If you take a square tip, for example, like they do on a Mooney there, or the early Moonies, this air coming around here rolls over and picks up a vortex, and the vortex can't get around this sharp edge, and it's actually further out. This will actually have a plus aspect ratio for you because of the fact that it forces the vortex to get further out in here. It's a question of whether this is an actual reduction in drag. It is a slight improvement of aspect ratio, therefore a slight improvement of induced drag, but it may be actually an increase in total drag because maybe your profile drag now has gone up due to the squareness of this tip. It has to be looked at very carefully. I would say if the tip tapers back and away as it goes downstream, then it's going to be worse. If it, on the other hand, has a little bit of a positive gradient to it, it might not be as bad. It has to be looked at real close. But one of the things they did find out, that if they took the ordinary tip they had and put a wing tank on it, like the early P-80s had, This round tank in here caused the vortex to really roll way inside in here, and this wingtip hanging down underneath there was a definite disadvantage and definitely hurt the performance of it. So that's why later on you saw that the wingtips were put on pretty much in the center of the wing rather than hanging down underneath it, and this gave a little bit increase in the aspect ratio. But what Horner really did find, what the final conclusion of the whole thing was this. He found out if you have the top of the wing here and the bottom of the wing here, it's got to end someplace. You're going to have a vortex no matter what you do, but everything you can do to throw it out as far as possible smoothly is the best you can do. So what he found is that if you kept the top in here and brought the bottom down underneath like this, that the air flowing down underneath here would be thrown out and throw the vortex as far away as it possibly can based upon the conditions that you're operating on, and that would give you the best optimum wingtip. A Lockheed Connie, for example, Constellation, has a tip that is designed almost exactly the way Horner demonstrated that it would be an improvement on it. But the interesting thing is, he showed that if you went from the worst wingtip to the best wingtip, everything else being the same, you would have a 2% increase in range and a 2% increase in rate of climb. No major changes, no big significant changes, but definite improvements, but 2% is about the margin you can be working with. There is, of course, some things as winglets. Now, the winglet is really the very best way that you can work with the handling the tip itself. And this is a case where you have, looking at it again from the front view over here, you have one surface that's sticking up the bottom, another one on the bottom, and from a side view, the upper surface might be canted off in this direction, and the bottom surface might be canted off in this particular direction. What we're doing here, without getting into a lot of complication at this point, since the air is going to be swirling in here, by taking an airfoil section and canting it in just a little bit so that actually from a top view, looking down from the top in here, and I'll exaggerate, this airfoil is pointed where the leading edge is further out at an angle of attack to try to capture some of this flow that's coming in and producing a vector inward, which part of which is forward and part of which is back. If we wanted to break it down, the free stream is coming off in this particular direction in here. Then we'll find out that we get a slight thrusting of the thing, is very minor, but at least a reduction in drag that goes with it. And the same thing with the bottom. The bottom of the airflow is flowing the other direction with it. But the best you can do on a winglet is design the area and the angle of attack of these surfaces for a particular lift coefficient or a particular angle of attack. And if the airplane is going to cruise along like a cargo airplane might or an airliner might, always flying at one particular speed or particular angle of attack, then you can make your winglet work very, very nicely and give you the best efficiency. Any other speed, faster or slower, the winglet is not working nearly as well as it would have before. Actually, if you took the same amount of area and if you canted it down over here and made it stick out horizontally here, that would be even better yet, no question about that. But of course what this does, what's wrong with this is the fact that this is giving you even lift now, and it's increasing the bending moment of the wing of the spar of the wing, and therefore that adds to the stresses that are in the wing or reduces the amount that the wing can actually carry or the G-loads that it can tolerate. So when you're fixed and you can't increase your wingspan any more than what you have, the winglet might be another way. But if your airplane is going to fly at a variety of speeds and a variety of lift coefficients, the winglets themselves won't do you much good. If you happen to have a canard type airplane like Bert does with his different designs, where the wing itself is in the back and you can use these surfaces and give you additional directional stability, fine, great. Now you're getting two things for one, then it's well worth it. Because even if it hasn't done much for improving your induced drag or reducing your vortex on it, it has given you some benefits as a directional stability device. So these things need to be looked at. The winglets are a very, very good feature. They can't do everything for you, but they can improve it. They're somewhat sensitive in how you design it, but if we work at it, you can get a definite improvement with that. The other thing you have to look at when you start looking at drag coefficients and looking at the actual value of them is where are these particular items associated. For example, if you have one strut flying through the air and you put another one behind it, there is various distances that are better or worse. There are some places where you can have one strut right behind the other flowing through the air, where the drag coefficient of the rear strut now, or the total of the two, is worse than just doubling of any one of them. So the drag of the back one is even higher than it would have been if it's out in free stream. Same thing as if you have a strut or something very, very close to the fuselage or the top of the wing or something like that. You will have definitely an interference effect. I mean, that's what you have to call it, interference. But it's really changing the drag coefficient of either that particular item or the body that's associated with there. I think a lot of you remember seeing back in the late 1930s when the racers were running around and the Thompson Trophy races and so on, and they had fixed landing gears yet on it. And from a front view, we could see a wheel like this. The typical thing would be to have a strut coming up in here. Well, they recognized in that time that this region in here caused even greater interference and therefore caused a lot more drag than these two items separately. So what they did is they would change the strut and bring it out like this and then up in this direction in here. And then this interference and the association of the strut against the wheel had the minimum amount of drag that you could get with this thing if it had to be there, if it had to be out and exposed. So when you look at the shape of the object, you find the drag coefficient of it, but then look where that object is and where it's associated with. For example, you'll find an awful lot of airplanes that have a windshield canopy like this. And what do they like to do? You like to put your doggone big tube sticking up over there for measuring your outside air temperature, or you want to install an antenna. You install it right up on here. This is the absolute worst possible place you could do it. For one thing, as the air flows here and goes over this object, it speeds up. It's going at much higher speed than the rest of the airplane is. Putting a particular item here, the drag coefficient is still the same, but the velocity that it's associated with is much higher. Therefore, the total drag is much, much worse there than if you would put it on the belly of the airplane or somewhere way back on the rear portion of the fuselage in there so that the velocity isn't at its maximum. So these zones are something to really stay away from. Same thing with the top of a wing. If we're looking at an airfoil section in here, don't put anything in this region in here. This is the absolute worst possible place you could do it, because not only is the velocity very high and that you're increasing the drag of whatever you happen to have sticking up over here, but the fact is that you are dealing with very sensitive air here as it's trying to lift the wing, and you can get flow separation and not only drag, but loss of lift. So this is a zone absolutely stay away from. This zone here, if you have to do it and you have to stick something out, that's a good place to do it. Put it over there. Watch very carefully where any of your disturbances might be, and you will see that you can definitely have the minimum amount of drag of a particular object that has to be sticking out into the airstream. Obviously, you can submerge it and bury it inside there, eliminate it completely. That's the best of all things. We've all seen what fillets look like and fairings look like, where a wing meets the fuselage or the tail meets the rear part of the fuselage, something like that. The fact that we want to put a nice smooth juncture in there is important. But when we're dealing with the wing to fuselage, we actually have something that's relatively sensitive there. Because what we're doing is not only do we have the interference of two bodies meeting each other, but we have one body that is trying to lift, produce lift at this particular point, and the fuselage generally after it passes the wing starts to narrow down. So we have a triple jeopardy, if you want to call it, in that particular region. Let's take a look at this interference of the wing to the fuselage. And if we would take a look and see a wing section that might look like this, coming out here, and a fuselage going back in here, and let's assume it curves up and goes back. Okay, we all know that this region in here we want to put nice smooth fillets to make it nice and round, to have a nice smooth intersection between the fuselage and the wing itself. But we're starting to run into the real critical zone now. Number one, as we start to get over the top of the wing and the wing section starts to go down, the air as it flowed over the wing producing lift is now starting to slow down, and it's in a very, very low pressure region. It's very weak in energy. It doesn't really want to stick to that wing. If it separates, we're going to have a lot of drag and we're going to have loss of lift. So we don't want it to separate. If, on the other hand, we have this side of the fuselage in here and its boundary layer is building up, and the boundary layer is building up, by the time it gets to here, these two are going to get very, very thick. If we look at it from an end view, here's the boundary layer of the fuselage, here's the boundary layer of the wing. Where these two meet in here, this is a double zone in here, so it's very sensitive. So if we could curve it, that's fine. But as we get in this region here, we have to make sure our curvatures are getting bigger and bigger and better, because it's getting very weak, and we can't have a gradual curve. We have to have a very large curve like this. But right when we get into here, right when we pass the wing, this is when the fuselage likes to taper too. So now, here's the side of the fuselage, the air was flowing. It now has to start curving inward too. The wing, on the other hand, is curving down. So one of the best things to do is to change this region of the wing right here. Instead of having this airfoil remain the same, put a little reflex to it. Bring the upper surface in this way and curve it down into here like this. So that from a particular side view, if this is our actual airfoil right in here, when we get right up against the fuselage, we've actually curved it like this. Now you can see what we're doing. By curving it up, instead of making a flap coming down, we're actually putting a flap upward in here. We're not trying to force the air to flow over the wing as much. We're not making it as critical. And combining with the boundary layer there, we will then end up with a very, very nice solid fillet and very, very possibly not have any separation whatsoever from this particular juncture. It may have to come back in here. You may have to make your fillet a lot bigger into this region. And from the side view over here, this might be the parting line. This is the upper surface of your fillet right in here, and then this is the lower surface of your fillet right in here. But this is a very neat, unique trick that you can put to the interference. You don't necessarily have to do this at control surfaces, the horizontal tail or the fin and rudder back in here, because they are not at high angles of attack most of the time. But the wing, you really want it to lift practically all of the time. You do have it at a positive angle of attack. It does have sensitive air in it. Reflex the trailing edge just as it gets up against the fuselage. Put a nice fillet into this zone in here, and you'll end up being sure that you keep attached flow to it. This is one region you want to check with tufts right away, because it's very easy to get flow separation off it. Whatever it takes to do to keep the air attached to the wing and to the fuselage is very, very, very important. If we want to take a look at what all of this means to the airplane and how we can actually calculate the thing, we can go back and use some basic formulas and take a look at what it actually would do. Let's, without getting into a lot of technical engineering stuff, let's take a look at the basic formula that is used in determining the drag of an airplane or any particular surface itself. If we take a look at the drag itself and want to determine what its actual force is in pounds, we will see that we can call it a drag coefficient times the density ratio times the area by the velocity squared over 391. The velocity in this particular case is miles per hour. This 391 transfers all the units over so that your drag actually comes out in pounds. Your drag coefficient itself is in a non-dimensionless unit, the CD itself. This is the density ratio. It's 1 for sea level, and to start off with, that's always what you can use. You look up in any of the handbooks and you'll see what the density ratio is as it goes up into altitude. For example, around 1,700 feet, it's somewhere around 0.79 and so on. This, again, is the area of the particular surface you're talking about. If you're talking about the wing, it's the planform area. If you're talking about the fuselage, it may be the frontal area. It may be the total wetted area, the total skin area of it. Whatever this drag coefficient is based on is what you want to use that. In fact, this CD here itself times this S is equal to this flat plate, equivalent flat plate area, or sometimes you see it as D over Q. Q being the dynamic pressure of air, 1/2 rho V squared. Any one of these things, they all mean the same thing. This is the unit you want to work with when you go in here. When you're dealing with the drag coefficient of a complete airplane, you have to really break it down into two things. This is the CD based upon profile area and based upon base area. It's your standard drag coefficient as it expands with the total of the airplane, but it has nothing to do with the induced drag. The induced drag, on the other hand, is a separate factor, so you generally have to break that down so that when you would want to plot these things, you end up with the drag over here and the velocity over here. Your induced drag is the highest at the slowest speed and gradually goes down. Your profile drag starts at 0 and gradually goes up. And it's the summation of these two things that will give you what your total drag polar is going to look like. If you take Perkins and Haig's book of airplane performance, stability, and control, you will find that this book itself is probably one of the best ones to describe you how to calculate your performance, how to get your drag coefficients, how to use your drag coefficients on your drag polars and your power polars. It's a very, very good textbook. We won't take a lot of time now to go through that, and just except to say that this is how you eventually use all these things if you want to calculate precisely what the drag in pounds is. Once you know the drag, you can take the drag times the speed in miles per hour divided by 375, drag in pounds again, speed in miles per hour divided by 375, and that gives you the horsepower required for any particular speed on a thing. I think what we're going to do now is take a good look at how we can apply these things to actual units. I'm going to go through it a little bit fast here. We're going to use a Bede as an example, but you can actually get an illustration of how you can take a particular airplane, calculate all of the different factors in it, what the drag coefficients are, and what it will actually mean in pounds of drag and total horsepower for your airplane. All right, let's take a look at the Bede, and let's take a look at the wing drag to start with. If we use S to denote the planform area of the wing, the total wing area is 104 square feet. But the actual exposed area, you have to take the area away from that the fuselage consumes, because only the part of the wing that's sticking out on either side is the exposed area. It's 90 square foot of wing area, so we'll end up using that. Our average chord, or mean aerodynamic chord, is 4 feet. We're using a 64-415 airfoil section on it. So one of the first things we want to do is to check the Reynolds number. If we use these two equations here for determining the Reynolds number, this one is what it would be if you're using knots. This is the equation that it would be if you're using miles per hour. In our case, for example, here, we're going to be using a 4-foot chord, and we're going to be talking 150 miles per hour. Our Reynolds number is 7.4 times 10 to the 6, or 7 million. The CD, based upon NASA's TR-824, the drag coefficient is 0.005 for that airfoil section. But one thing we have to remember is that we actually have this thing in the real world. There will be some bugs on it. Even though we made the wing very smooth and nice, there may be some cracks, some little imperfections. So I think realistically we ought to go ahead and increase that drag coefficient, well, in this case 20% even. We're going to go from 0.005 up to 0.006. So the F number of the wing, which is the drag coefficient times its area, will be 0.006 times 90, which is the exposed area, gives us an F number of 0.540. Now let's take a look at the fuselage drag. The fuselage area, based upon the frontal area, is 12.8 square feet. If we go ahead and determine the fineness ratio, which is the relative ratio of the width to the length, we use that by finding the length on top and the diameter on the bottom, but since it's not round, it's square, we can use a simple little equation of this 1.128 times the square root of the area of the fuselage. So we take the square root of the area, and the final result is that our fineness ratio is 5.2. If we go ahead and look up on the charts of what a streamlined body would be with a fineness ratio of 5.2, we'll find out that the drag coefficient of the fuselage is 0.062. Now this is of an average set of fuselages or nacelles or streamlined bodies going through here. In other words, some have rivets on them, some have gaps. These are not super smooth glass lined streamlined bodies, but instead they're real fuselages. And using that chart, we find that the 0.62 drag coefficient is a pretty good one to work with. If we now want to calculate the F of the fuselage, we do that times the equivalent area, which is the frontal area we're talking about. We end up with the F number of the fuselage of 0.793. All right, let's look at the horizontal tail. Here again, we have a horizontal tail that has 28 square foot planform area, but the exposed is 26.8. The airfoil is a 64012. It has a drag coefficient of 0.005 in the books. Let's assume again we have some imperfections, therefore we're going to use 006. The F number of the horizontal tail is the CD times the area, 0.006 times 26.8. We end up with a 160. All right, let's look at the vertical tail. Here again, the exposed area of the vertical tail is 16.5, and in this particular case, that's exactly the total area too. The airfoil is a 64-12. The CD, same thing as 005, but we're going to use 006 because we do have a gap that we have to worry about on there. Our F of the vertical tail is 006 times 16.5, which is 0.099. All right, now let's take a look at the wheels. In our main gear, we happen to have a strut sticking down, which is 26 square inches, which is 0.1806 square feet. For both of them, it's 0.361. The wheel area, the frontal area of the wheel, is 1.66 square feet. That's the total of both wheels. In the case of the nose wheel, we have a strut, which has a 0.1649 square feet. The wheel area here again is 0.2778 square feet. Now, if we take those set of numbers and start applying them, we can determine the F number. But first thing we have to do is determine what would be the drag coefficient. First thing is, if we have a very streamlined shape, we're going to have a drag coefficient of 0.07 based on the frontal area. If, on the other hand, we have a rectangular one with rounded corners, we're going to have a 0.5 drag coefficient. But if we have a square one with sharp corners, we're going to be way up to 0.9. Well, obviously, let's take those doggone landing gear struts, let's make them somewhat streamlined, and now we're going to have the F number of the main strut would be, if we use 0.07, 0.025. If we use a 0.5, it'll be way up to 18. If we use a 0.9, it'll be 0.32. So obviously, we want the lowest one. Let's go to 0.025 as the total F number of the main struts. The main gear, the wheel itself, we'll find that the CD of it is 0.22. Based upon the frontal area, the F number now will be 0.365. The nose wheel and its strut, here we are with 0.10. We have the area of it, and there's our total F number. It's not very big, but we got to use it all the way. And the nose wheel itself, doing the same thing. The CD of the nose wheel is 0.22 times its frontal area gives us 0.061. Now, if we go ahead and start adding these things up, and that's all you really have to do is add them up. The wing, fuselage, horizontal tail, vertical tail, landing gears, we come up, it's a total F number of 2.0595. But we really should add about 5% interference drag on here. Now, you got to be careful how you're doing your interference drag. In the case of the Bede 4, it really has good intersection joints. The wing meets the fuselage very, very nicely. It's a squared off side of the fuselage on the bottom. The top of the wing flows in absolutely smooth and completely, so we have no flow separation at its intersection. We have the tail, horizontal tail, and the fin in the back meeting it, but already the boundary layer sticks, so it's not too critical there. But one of the things we have to remember when we're using percentage like this is the Bede 4 itself is a pretty low drag airplane. So 5% of a low drag airplane is a certain unit, which in one case is a very large number if you would take 5% of a very, very dirty airplane. So when you're starting to multiply your calculated F by a particular percentage, rough estimate in there of what your interference is, take into account. If this was an airplane with very, very, very long wings like a sailplane where the wing was the major part of your total drag, then your interference number would be even smaller. So in this case, we're using 5%. We would end up with a total F number of 2.1625. When we go ahead and put speed pants on it, fairings where the wheel pants come in and completely enclose the wheel, we actually drop the total F number down to 1.69. Ah, I'm sorry, I'm giving you some wrong numbers in here. Yeah, this is with the speed pants, this is without it. You can see it's a significant difference just by putting the speed pants on. When we actually did the flight test on the airplane, we found out that the best we were able to measure is that our total F number was 1.84. So it's close to what we've actually calculated here, and if we go back and analyze very carefully, we could find out that maybe instead of 006 for the wing, it was really 0058 or something along those lines. But the end result is that you can, once you've done these calculations, built the airplane, go out and fly it, we can get into how you flight test it, and you can determine pretty accurately what your total drag coefficient of the whole airplane would be. But here's a good set of formulas, relatively simple. You don't have to be an engineer that has gone through many, many years of school to be able to adapt these and put them into good use. You have to be careful on what you're doing with it if you're not really familiar with them, but it will give you a good start in how to work with it. So when you're dealing with the drag reduction of any airplane, whether it's a home-built or a production airplane, look at all the little things. Some of the little things may turn out to be quite large. Many of the things you can do are rather simple, rather easy to take care of. Obviously, the simple thing of waxing the airplane, putting a good paint finish on it, sealing gaps. This is always an important thing. Anytime you have a connection with a panel or something like that, if there is an opening there, if air can flow in and out, you don't see this air going in and out. You don't have any drag coefficient for it. But if air is going in or it's going out through that gap, it is creating drag. It is producing some additional loss of energy of the airplane. Seal it up good, make it airtight, and you will improve your airplane quite a bit. We can take the total airplane drag coefficient and carry it a little bit further in developing the actual power required curves. The one thing we'd like to be able to add to all of this in determining the power required is the actual cooling drag itself. But here we might want to use it in a little different way. Instead of breaking it down into a drag coefficient, it'd be good if we broke it down into actual brake horsepower required for cooling. This would be the actual equation you could use in determining it. The horsepower required for cooling will be dependent upon the cooling airflow in actual pounds per second, the speed at which you're going at in feet per second, the exit speed coming out of the cowling itself. So you have the forward speed subtracting the exit speed coming out times that upper term, divided by 550 and G, which is 32.2 feet per second squared. Now this is the actual equation, and you can do this for different speeds. Of course, you have to know really what is the speed of the air coming out of the cowling itself, and you have to know the number of pounds of airflow that is flowing through the cylinders per second to be able to use that equation. It's a little bit complicated, but it can be done. It does give you good accurate results. But another way of doing it is just to take the actual propeller efficiency and lower it by 3 to 5%. This percentage is good in the normal cruise range, climbing condition and cruise condition, not necessarily right on takeoff or slightly above stall or anything like that. If we would do that, if we take that original drag coefficient we do of the airplane, apply it to this equation, we can then develop the actual power required curve. And in this case here, we're talking about the power required would be equal to this term here plus this term. F again is our total equivalent parasite area, which is the airplane's drag coefficient times the appropriate area, which is normally the wing area. The speed now in miles per hour. E, the Oswald efficiency factor, and it's always good to start somewhere around 0.8, 0.85. The gross weight of the aircraft, and B would be the span of the aircraft in feet. By knowing those terms right here, applying it into this equation, you'll end up with a plot that looks something like this. And this will tell you the actual horsepower required for that particular airplane to go at any particular speed. Now, propeller efficiency is taken off by the power available. That's what the engine's going to produce. So once you know the size of your engine, the power that you have, the losses due to propeller efficiency, and then subtract a little more for engine cooling, you'll be able to see what the two curves, the power available and the power required, actually cross, and that'll give you your maximum speed, which you can cruise at. And the difference between the two will give you your excess power, which will determine your best rate of climb.